to continue to talk about time complexity, how long it takes an algorithm to run. So let's look at our linear search algorithm, and let's think about trying to search through this array of class marks that are not sorted. So suppose we were trying to search through this array. The linear search is very simple. It just starts at the beginning and it goes through each element one at a time, and in this algorithm it just continues right until the end. No, as soon as it gets to it, it will return it'll return the index of the element as soon as it gets to that element. So basically, if we pass this into linear search and we asked it to look for 52, it would start at 0, at index 0, and it would find 52 and it would return index 0. So suppose we were looking for 52, this just did it in basically one step. It just had to start the for loop. It did one comparison, it checked if the array at 0 was equal to the element at 52, and it was true, so it returned I. Suppose we asked it to look for 78. Well, it would first check 52. Nope. Check 94. Nope. Check 100. Nope. Check 67. Nope. Check 78. Yes, 78 is equal to 78. So how many steps did it take to get to that? Basically 1, 2, 3, 4, 5. It took about 5 steps. Now, if we had more class marks, maybe we had the class marks for every single student in all of Canada in every single course, that might be like 40 million marks. So if it had to go through and find something in the search, it's possible it might take 40 million. That's the absolute worst case that could happen. So if the size of the array class marks was size n, then it could possibly take n times to get to it. So we're going to use notation like this. We're going to say that this O is our time complexity, and in this case it has a complexity of size n. We're generally going to always put our function to represent the complexity in terms of n, the size of the array, or the size of the information being passed in, the data being passed in to an algorithm. And then the big capital O here represents our time complexity. So our worst case here is size n. Best case is 1. Probably not very likely. Average case is n divided by 2. Now generally n divided by 2, because at least half the time it should be in the middle-ish. It should average out to that. If we were to have n over 2, generally all we really care about is the variable and not any coefficients with the variable. And for example, if we were to figure out that something was going to take n plus 1 steps, we ignore the plus 1. What's one more step? We really care about what happens when n becomes a very big number. If n's a million, the fact that it's a million is way more important than a million plus 1. So we don't worry about any constants that are being added. We also don't worry if there's a coefficient, a number coefficient. We just focus on the actual variable part. Okay. Now, if we were able to figure out the worst case was actually n squared plus n squared is going to get bigger much, much, much faster than n. This is a parabola, and n is linear. If we look at these two functions separately, here is my parabola, and here is my linear function. The parabola gets so huge that just adding a little n to it isn't going to make a big difference, so we're more concerned with the n squared. So we take the worst